sophomore at Yale University, and I'm a mathematics major student. And at the same time, I'm also thinking about pursuing a double major in economics. So today I will give a lecture on the design of the train track system, the minimum spanning tree problem. This is actually from a class I took last semester, which is the discrete mathematics, but I think the topic's really interesting and will be really helpful for all the students here. So I would love to share with you guys. Okay. So this is the general outline. So first I will state the problem of the train track system, and then I will provide the mathematical formation, which is the minimum spanning tree problem. Then I will probably give some definitions to help the students understand this topic better. And also I will try to give some algorithms to solve the problem. And we will also do some problems for the students, and also I will mention some real life applications. So first of all, we can think about the job of a railway company. For example, we need to connect some of the cities in a country, and then we know that for the distance between each pair of the cities, so that we can try to find in what way should we build the railway system. So as a company, I want to connect all the cities in the list so that we can travel to any of the cities. And also at the same time, for example, I hope the total distance will be the minimum one, because the longer the railway system is, the higher the cost will be. So I'm trying to reduce the cost, and thus I want the distance to be the minimum. So here's an example. This is a map of the United States, which is around the New York City. So here, for example, I will choose 4 cities in this map. For example, Albany, Springfield, New Haven, which is where Yale University is at, and also New York City. So these 4 are the list of the cities that we have, for example. And then we kind of consider all pairs of the cities, like as I have shown on this graph. It's like we have 6 pair of cities from Albany to Springfield, from Albany to New Haven, etc. So I kind of show this as the map for our problem. For simplicity, I will simply use segment, like straight lines, for the statement of the problem. But it's like we only cares about the pair of the cities rather than whether the track is straight or not. So it's totally fine if we can draw it in another way, but that's how we build this problem. And then we also, by the use of Google Map or some other really helpful applications, we can get the distance between each pair of the cities, as I shown on the graph, which is in the units of miles. So for example, Albany is 85 miles away from Springfield. Okay, so this is our statement of problem. Is there any questions right now? Sorry, I cannot see the chat screen, but yes, okay. So now let's focus on this graph, and I'll make a copy of it. So we can think of how we can build the railway system to connect all the cities. For example, if we connect all 6 pairs of the cities that is away, so that, for example, if I'm at New Haven, I can go to anywhere in this map. But it's like there are some of the tracks are redundant. It's like we do not need to have the pair of the cities there. So let's try some different examples. For example, let's use the Albany as the central city and connect every city to Albany. So in this way, we can kind of form a railway system, and actually from whichever city you are, you can go to another city easily. So in this example, the total distance of this railway system is 365 miles. So this is just one example. And we can also think about, let's form an S-shaped railway system. For example, to go from Springfield to Albany, and then to New Haven, and then to New York City. So in this example, the total distance will be 290. It is shorter than the previous example. And then we can, but it's like we can think about a smaller one. So this is actually the smallest plan for this for this example. So we can build the railway between Albany to Springfield, and then Springfield to New Haven, and then New Haven to New York City. So in this way, the distance will be 225 miles, which is the smallest distance to connect all the cities in a railway system. So this is actually a really interesting problem for us. So we want to think about, given a list of cities, how can we build a railway system so that we can connect all the cities with the minimal distance. And yes, so actually it is a mathematical problem, so which is called the minimum span tree problem. So I'll show the mathematical formation of this problem. So that G, which is graph, the G here stands for graph, equals to a pair of V and E, which is vertices and edges. So be a connected graph where the V the vertices stands for the cities, and at the same time, the edges stands for the possible train tracks, or we can say the pair of the cities. And then we can denote a weight function, the W, so that we can just make it to so that we can kind of show the distance or the weight we put for every pair of the cities. So this is simply a function. Like we see in our previous example, here we have 65 for the edge between Springfield and New Haven. And then we can, what we need to do is to find a spanning tree T of the graph G, such that the sum of the weight will reach the minimum. So this is the mathematical formation for our problem. But I also noticed that there are some special terms in the mathematical formation. For example, connected graph and spanning tree, which perhaps most of the students here are not familiar with. So I will go through the basic concepts of the graph theory. So first, what is a graph? So a graph is actually an ordered pair VE, where V is a finite set and E is a set of two-element subsets of V. So in another word, V is the vertices or the cities in our map. And so here, by saying a finite set, we want to show that there are finitely many cities or finitely many vertices in this graph. And then E, which stands for edges, is simply a set of two-element subsets of V, which means that, so in another word, every edge connects two cities, or two vertices. So it's like if we simply give the two vertices for this edge, we will get to know which edge it stands for. So for example, if we simply give Springfield and New Haven, we can know that this edge is denoting the edge between Springfield and New Haven. And let me give some examples of the graphs. So this is one. So it's like we have four edges here and also four vertices. So as we've shown, the edges are the edge between Albany and Springfield, Albany and New Haven, Springfield and New York City, and New Haven and New York City. So there are 4 edges. So this is simply an example of a graph. And here's another example. So in this example, we still have 4 different vertices: Albany, Springfield, New Haven, New York City. Here we can see that we have 6 edges. We connect all pairs of the cities, all possible pairs of the cities in this example. So it is not simply a graph, but also a complete graph, which means that we connect all the possible pairs in this graph. And then what we see in our example is, in our mathematical formation, is the idea of connected graph. So what is connected? First, I would love to introduce the concept of a walk. So it's a bit mathematical here on the slides, but in a simpler way, I would say it is simply like, for example, in a graph, we want to find some walk between from Albany to New York City, which is from, I don't know whether you can see my mouse or not. So from here, the upper left to the to the down left. So we actually have 2 different paths or walk to go from Albany to New York City. The first way is go from Albany to Springfield, which is the upper right, and then go to the New York City. So this is a walk for this graph. And then another walk would be Albany, and then New Haven, and then finally goes to New York City. So these are 2 walks from Albany to New York City, just for example. So we say the graph is connected if there's a walk between any pairs of the vertices. So in this example, we can see that we can choose whichever 2 vertices in the cities, and then we can see that we can actually go from one of them to the other easily. Is there any questions by this far? I'm not sure. Let me see the chat, sorry.
Yes, if you have any questions, please feel free to send them to one of our staff members. Roger's having a hard time seeing the chat.
Okay.
We don't have any questions so far.
Okay, great. So let's continue. So here we know about the ideas of the connected graph and also simple ideas of graphs. So what is next is I want to help you know about what is tree, as we are discussing the spanning tree in this problem. So before define the tree, I would like to share what is cycle. So a cycle is actually a walk, first of all. But in this walk, the start of the walk is the same vertices or city as the end of this walk. So in the mathematical way, it is like the V0 equals to VK. So in this walk with K plus 1 different vertices. So for example, in a graph, we can see we can go from Albany and then to Springfield, New York City, New Haven, and then back to Albany. So this actually forms a cycle. So, and we also see that there's we are following the path we are given on this graph, and also we didn't go backward. We didn't go same track twice. So this is a cycle, just a brief example. So what is a tree? So by definition, tree is a graph which is connected and does not contain any cycle. So in the previous example, in this example, we can see that it actually forms a cycle, which is shown on the slides also. So it is actually not a tree. So I will also show some of other examples to help you understand what is a tree. So in the first example, it's not a tree. As we shown in our previous slides, it forms a cycle. For the second one, it is also a graph, but it is not connected. As we can see that if I'm in New Haven, I cannot go anywhere else in this graph as there's no edges connected to New Haven. So it's not a tree as well. And in the third example, it is a tree. It's connected. All the four cities have edges to another, and we can go from every city to another one. And also, we can see that there's no cycle in this example. The fourth example is also a tree, as it is connected and it does not have any cycle. So this is the definition of trees. And then there's also a really useful formula or theorem for the definition of tree, which we will use in our later example. It is called Euler's formula. So this formula tells us the number of the vertices in a tree is 1 more than the number of edges in a tree. So we can see from our example on the right. In both of the examples, we have 4 vertices, the 4 cities in our graph, in our example. And also, in these 2 examples, we only have 3 edges rather than 4 or 2 or other example. So in Euler's formula, or this theorem actually tells us if it is a tree, we can have this relation between the number of vertices and the number of edges. And at the same time, if we are given that the graph is connected and also the number of vertices is 1 more than the number of edges in the tree, in this connected graph, then it is a tree. So we can actually go both sides of this theorem. And lastly, it is our definition, the spanning tree. So let G be a connected graph as is shown on the left side of the graph here. And T will be a subgraph of G, which means that it has all the vertices of the original graph, and all of its edges in the subgraph is a part of the original graph. And then we can see that T is a spanning tree if T is a tree and T contains all vertices in G. So in this example, we can see that on the right-hand side, we can see all the 4 cities are covered in this graph, our spanning tree, and at the same time, it is also a tree as it does not contain any cycles and it is connected. So this is just the example of the spanning tree. As we can see, the graph on the right is actually a spanning tree of the graph on the left. Okay, so we have done all our concept introduction. So it's like we have covered almost all the things we need to for this problem. So let's go back to the minimum spanning tree problem again. So there are actually many different algorithms or methods to solve this problem. And 2 of the most famous ones are here. So the first is Prim's algorithm. This algorithm is developed in 1930 by Czech mathematician Wojtek Žáček, and then it is actually rediscovered and republished by computer scientist Robert C. Prim in 1957 and Oskar W. Dijkstra in 1959. So actually this algorithm is named after Robert C. Prim. And then another really famous algorithm is Kruskal's algorithm. It is written by Joseph Kruskal, and it first appeared in his paper in 1956. Both of these algorithms are also called greedy algorithms, as in the process, as we will shown later, it always tries to find the minimal edge in every step of the process. So first of all, let's let's check the Prim's algorithm. So it will initialize a tree with one single vertex chosen arbitrarily from the graph. So for example, we have four edges, four vertices, four cities in our example, and we can choose any one of them. Any one of them is totally arbitrary. And then we can grow the tree by one edge each time. So we will choose the edge from the edges that connected to the tree we have to the vertices not yet in the tree. And then among these edges, we will find the minimum weight edge and transfer it to the tree. And then we will keep on repeat the step until all the vertices are in the tree. Or in another way, we simply need to add n-1 edges, where n is the number of vertices. This is because of the Euler formula, as we see that the number of vertices is simply one more than the number of edges. So, okay, I'll use our example to illustrate this algorithm better. So, for example, we can in the first step, we can arbitrarily pick one vertex. For example, I'll pick Albany. So, and then we can see all the edges connected to Albany, which is the upper left in this graph, to all the other three cities, which is Springfield, New Haven, and New York City. And in these three edges, their weights are 85, 130, and 150 separately. So we will choose the minimum weight one, which is 85, the edge between Albany and Springfield. And then we will add this to our tree. So now our tree are shown in red in this slide, which consists of two vertices, Albany and Springfield, and an edge between them. So the next step is, again, we need to consider the other edges which connects the vertices in our tree and those which are not in our tree yet. So in the previous step, we have Albany and Springfield in our tree. So we can see that all the edges connecting these two cities, one of these two cities to New Haven or New York City. So there are four edges in total, and the one with the minimum weight is the edge between Springfield and New Haven, which weighs 65. So we will also add this edge to our tree. And then the last step is to connect an edge to the New York City. So, and we also see that the minimum weight one is the one from New Haven to New York City. So we will also add this edge to our tree. And then we can see that this is simply our minimum spanning tree for our example. So what if we pick another initial vertex rather than the Albany? So for example, we can pick New Haven in this time. And then we will go through the steps again. So we will see that the edges connecting to New Haven will weigh 65, 75, and 130 respectively. And we will pick the one with 65. And then we will consider all the edges connecting New Haven or Springfield to Albany or New York City. And we pick the minimum one, which is 75, the edge between New Haven and New York City. And finally, we will pick the last edge, the edge between Springfield and Albany. And again, this gives us the same tree in this example. So we can also think about some other examples. So this is a pentagon. And so the reason why I picked this example is we have some of the edges in this graph with the same. So there are two edges weighing 3 and two edges weighing 5. So we can, again, we arbitrarily pick one vertex, let's say C, and then we will pick the minimum weighing edge, which is CD in this example, and then D is also included in our tree. And then we may go one step further. We're not sure here. So because the edge DA and DE are weighing same here, and also they are both the minimum weighing edge. So we can pick one of them. So we can either pick DA as I have shown in this in the slides, or we can pick DE. It's totally up to you. So in this example, I will pick DA. And then we can see A is the next edge. And then finally, we can pick AB or CB to include B in our example. And then finally, it is our minimum spanning tree. Also a remark, there's more than one minimum spanning tree for this example, simply because we can choose between DA or DE, and also we can choose between AB or CB. So it seems that there should be 4 different minimum spanning tree for this example, but all of these minimum spanning trees gives us the same minimum distance for our railway network. Okay, so this is how the Prim's algorithm works. And I would love to proceed to introduce another algorithm, which is the Kruskal's algorithm. So first, we will list all the edges in ascending or increasing order of weights. And then we may add the minimum weight edge to the tree, firstly. So this is, and also at the same time, also the 2 vertices which the edge connected. And then we will grow the tree by 1 edge each time from the remaining edges that will not create a cycle when being added to the tree. So remember the definition of a tree, which is we will not create a cycle in the graph. So we actually want the adding edge do not create a cycle. So we will choose from these edges, and we will find the minimum weight edge and transfer it to the tree. And then we will repeat the steps until we have n-1 edges in total. So again, I will use our example. So in this way, in this example, we first arrange all the edges in ascending order. So as shown in the slides, from 65, 75, 85, 130, 140, and then lastly 150. So these are all the 6 edges we have in this graph. And then we firstly choose the shortest edge, the edge between Springfield and New Haven to the tree. This is our first step. And then we can see, we think about the second smallest edge, which is the edge between New Haven and New York City. We can see that it does not form create a cycle when added into in our tree. So we can simply put it in our tree as well. And then we will think about Albany to Springfield, which is the third smallest edge in our example. So we can see that it does not create a cycle as well. So we will simply put it in our example. So, and then we see that we have already added 3 edges to our tree, and remember we have 4 vertices in our example, so it actually reaches the end of the process. So this is our minimum spanning tree. Again, I'm also using this example to illustrate the ideas better, because in the previous example, in our example, we can see that actually the 3 shortest edge are simply the edges which form our minimum spanning tree. But this is actually a really special case. As we will see in this case, the case of the pentagon, we will see that it's not the case. So again, we arrange all the edges in the increasing order from A, E, C, D, A, D, D, E, A, C, A, B to finally B, C. So this is the first step. Okay, And then we add AE to the tree. So because it is the smallest edge. And then we add CD because it's the second minimum weight edge. And also it does not create a cycle. So here our tree or our graph looks a bit strange, but we will do it in this way. So it actually contains two edges which do not intersect or they do not share a same vertex. And then we can see, we will simply follow our order when we arrange them. So actually here, AD and D has the same value, but we put AD first. So let's consider AD first here. And we can see that by adding AD, we do not form a cycle again. So we simply add it. But here, when we consider the D as it is the fourth shortest or the fourth place in our arrangement, we consider about adding D to our tree, but we can see that by adding that, we actually form a cycle. So as we have included AE, edges AE and AD in our example, when we add the D to our tree, we will see that we can actually go from A to D to E to A. So in this way, we actually created a cycle in our example, which is not possible for trees or spanning trees. So we do not add this edge in our example. So the process continues. We consider the AC here, which weighs 4, but again, it will form a cycle. So we simply delete the edge. And finally, we will see that AB is satisfying and do not create a cycle. And then we reach the 4 edges, the number of 4, as we have 5 vertices here. So this is simply an example of the minimum spanning tree for this pentagon example. Oh, sorry. Yes, so this is how Kruskal's algorithm is working. So let's think about why Kruskal's algorithm gives us the optimal the result we need for our minimum spanning tree problem. So what we do is actually we arrange all the edges and we consider whether to add this edge one by one. And we kind of do this process from the minimum weight edge to the maximum weight edge. So in the process, we are actually doing one by one. And by adding each edge to our tree or our graph, we actually see that it is the best option. And in the bigger picture, we can see that finally it gives us the optimal one. So I have an example, and this is actually for all of the students, as we have introduced two different algorithms for this question. So everyone can try to solve this question. And so if you have the answer, you can simply unmute yourself and tell me what your answer is. You can use either Prim's algorithm or Kruskal's algorithm.
So everyone, please feel free to send our staff members your answers.
Okay. Does anyone get the answer for this or trial answer?
If you have an answer, feel free to speak up or send our staff members an answer. This is a pretty difficult problem, so we will give everyone a little bit of time.
Yes, as it's shown, it has 8 vertices and it's obviously more than any of our previous examples.
Ray, give him an answer. And Thomas, come on.
So is there anyone who want to share their answer?
Okay, we have one person working on the problem. Anyone else, if you find anything, please go ahead and say something or post on the chat.
Should I share the answer now or?
We're getting a couple of answers. So we have number 58, who said the answer was 15. Number 124, Richard, who says the answer is 16. Number 58, do we want to go ahead and share the tree that you found?
Yeah, just to say something. You can kind of show how you proceed to the answer you have.
Number 58, go ahead and just talk us through how you got 15.
First, you choose a point. I choose point A. Okay, from point A, I want to point F.
Yes.
And from point F, I want to point E.
Mm-hmm.
From E, I want to point G.
Yes.
And from G, I want to point H.
Mm-hmm.
And from point H, I want to point D.
Yes.
And then I want to point G, and I want to point B again.
Mm-hmm.
And from G, I want to C.
Yes.
Is that correct?
I think your path is correct, but I got a different answer. I'm not sure. I remember the one who got 16 is Richard, right? Do you want to share? Do you have the same
Yes.
same result? The same paths or edges with the previous one?
Richard?
A to F.
Okay, he says he has the same path.
Okay, yes, this is actually what I have. So what I got is the answer is 16, and the path is totally correct, but there might be some problem in the calculation. So it's a little bit pity, but it also tells us be sure to recalculate and to check our answers every time before submitting our answers. So maybe you have already get almost all the process correct, but you just simply did a small mistake at the last step and you got a different answer. So yes, I would say both of you did a great job in this a bit difficult problem. So lastly, I would put some remark on some real life applications for this problem. So for example, which we can see in telecommunication networks is actually a really important application of the minimum span tree problem, because all the telecom companies need to lay cables to connect each household. So they actually use the same methods to see which way the which laying cable way is the best one, and we have the smallest cost for them. And similarly, in the water supply network, that goes the same. We need to reach each household, and how to build this network actually is really important. And we can also see that it is important in computer networks. For example, when we build a tree model or some other model, we will put some weights and on different edges, or simply we can see by which network works better. So this is actually also a great method to check our computer networks. And finally, this is actually where this algorithm is this problem is first introduced, which is in electrical grids. So, and also there are many other applications, but these are some of the major applications of this example. And in our real life, for example, when we consider about the railway system, there might be more cities than 4 we need to take care of. So it's actually more complicated, and sometimes we may need the use of computer programming as other lecturers has mentioned in their lectures. But I will not focus on the realizing of the algorithm, but try to give you an idea of how this algorithm come from. And these are some of the reference I have for this lecture. And thank you very much. This is the end of my lecture. Thank you.